And this is the second video for week 3. In the first video we saw an overview of parametrizations and got some practice with at least one example with just a line. This video is going to focus on more parametrizations and talk about one important definition that we need. Just a reminder that parametrizations are not necessarily unique. As we saw with the line, we had 2 different parametrizations, and it's just some of them are a little bit more convenient than others. But just so that we can kind of get some common language going here, when we create a parametrization, what we're actually doing is looking at an interval for t, which is our parameter, or it could be s, whatever one you choose, and then the output is a path. So it's actually tracing along a certain region in in n space, where n is 2 or 3 or 4 or beyond. Okay, and that idea of a path, it really is just a continuous function in function okay, continuous function x vector x, such that we have vector x as a function where we go from some interval I, that is a subset of the real numbers, to Rn. And I'll just note that this here is an interval. Okay, it could be the entire real line, or it could just be a piece of it. Okay, so this could be something like 0 to 1. It could be something from like inclusive at 1 to 5. It could be all real numbers, etc., etc. Okay, and generally, in this course, when we work with parametrizations, they're going to be in either 2 dimensions or 3 dimensions. I would just like to point out that in this definition, the domain is an interval. Okay, and similarly, the range of the path is in n dimensions. Okay, and this is actually a curve. Okay, some sort of curve in n dimensions. Again, where n is generally 2 or 3. All right, so let's with that language in mind, let's go on to an example here. Oops. All right. So we're going to look at the unit circle and find a parametrization of that progresses counterclockwise from 1, 0. Okay, so I'm thinking I start here and I'm going to go that way around the circle. Okay, again, and I should have labeled my axes x and y. All right, and I think you might actually know a parametrization for x and y. Okay, if we think back to our previous studies, or maybe back to cylindrical coordinates, for example, or cylindrical coordinates, polar coordinates, we actually said that x and y was r cosine theta and r sine theta, where r is 1 here since it is the unit circle. So really we're just saying that the parametrization that we can use here is cosine of t, sine of t, where t is in the interval 0 to 2 pi. And we're not extremely picky about inclusive or exclusive here. Okay, so that's fine. And then as I progress t, it'll go around the unit circle counterclockwise. The next question, though, so it says find a parametrization that progresses clockwise 270 degrees from the origin from 1, 0. So I need to start up at 1, 0 along the y-axis and then go clockwise now about the origin 270 degrees. Okay, well, I still need to parameterize x and y. Okay, but in order to get that up at at the point 0, 1, I want you to just pause the video here and take a moment and see if you can find a parameterization that will allow you to start at that point and then progress clockwise. All right, and maybe you found it, maybe you didn't. Here's what I claim is the answer. Sine of t cosine of t, where t ranges from 0 to 3 pi over 2. Okay, and what you can do to check this is you can test some values. So when, for example, when t is 0, this is at 1, 0, 1, which is the point that we want. Good. And then when we progress to pi over 2, so I would be initially, I would start here, and then if I have t as pi over 2, I would be at 1, 0, so then it would go down over here. So I am indeed going clockwise, which is good. And then we could just check a few more points just to ensure that we're not making any mistakes. Just so happens that GeoGebra can do this as well. So if we're in GeoGebra, okay, just to show you that the first parameterization holds, what I did, so I just made a little bit bigger of a circle. I did a circle of radius 2 instead of circle of radius 1. And so I have a point P in here, and it's it has a slider functionality built in, where if I progress t from 0 and up to 2 pi, it makes one complete circle going counterclockwise. Okay. Now if I reset it to 0 and I hide p, I put a point Q in here where Q has the coordinates of sine t, comma cosine t. When I did that, and now I progress t, you notice I start up at 0, 1, and as I progress, it is going clockwise, and I can stop here at I think I can stop at 3 pi over 2 or so, and it would be right on the negative x-axis. Okay, so it seems like that function is working well. All right, so I think I've completed this example. We're going to do one more example in this video, and it has to deal with the ellipses. For this problem, I actually want us to fill in the missing pieces between the graph, the description, and the parameterization. So in the first one, an ellipse is given where the graph is shown, okay, and then we need to give the description. So I'm just going to go ahead and type this in, or you can write it in however you want. But this is going to be an ellipse with the semi-major axis, or I should say with a semi-major axis length of 3 along the positive x-axis, and semi-major or semi-minor axis length of 2 along the positive y-axis. Okay. The path starts at 1, 0 and proceeds counterclockwise. All right. So that is good, and I'm just going to do a little formatting here. I think. All right. Then in terms of the parameterization, this is where we might need to do a little bit of remembering or creativity here. So a cylinder, remember that it would be a three-dimensional object, and we can actually use that same idea here to help us with the parameterization of an ellipse. See if you can pause the video and generate the parameterization on your own. All right, and the parameterization should be, all right, we're going to have a vector x of t, and this should be 3 cosine of t, 2 sine of t, and I'll just say here that t is in the range of 0 to 2 pi. Okay. The reason for this is that what we can do is we can think of the traditional circle. So that would be cosine of t, sine of t. Okay. But we're scaling each axis a little bit, and that would be multiplying by the matrix 3, 0, 0, 2, which we learned back in Calc 2. All right, so that's the parameterization for this one, or I'll say a parameterization. All right, next one. This time we're given a description, and we need to generate both the graph and the parameterization. So it says an ellipse with semi-major axis length 3 and semi-minor axis length 2. The semi-major axis is rotated about the origin 45 degrees counterclockwise, and it's assumed it's from the x-axis. All right, so what we should have is an ellipse that, and I'm going to cheat here, I'm going to use the ellipse tool. All right, so we're going to have an ellipse, and it's going to be rotated 45 degrees, something like that. And so I know that we have a semi-major axis length of 3 and semi-minor axis length of 2. Okay, so that's kind of my diagram. And there isn't anything mentioned about where it starts its parameterization and rotates, or in the direction it progresses from there, but I'll just assume that it's progresses from that same place that we did on the previous one. All right. Then for the parameterization, it should look roughly the same as what we had before. So x of t, and then we had that 3 cosine, erase that, 3 cosine of t, 2 sine of t, but then it is rotated, and I want you to pause and remind yourself of the rotation matrix that we saw back in Calc 2. All right, and that rotation matrix should be cosine of the angle that we rotate by, pi by 4, and then cosine pi by 4 along the diagonal. Oops. And then we have negative sine pi by 4 in the upper right, and positive sine pi by 4 in the lower left. And that is our parameterization, along with the condition that t must be in 0 to 2 pi. All right. For the last one, I want you to pause and see if you can determine the graph and the description on your own. All right, hopefully you generated something that's useful, because the description here, and let's type it out. The description here is going to be an ellipse. Oops, let's get that in the right spot. An ellipse up 1 unit on z-axis in xy plane with major, I'll do semi-major, axis length 3 in y direction, and minor, semi-minor, axis length 1 in x direction. All right, so now we have to attempt to draw this thing in 3D and then we'll be done. All right, so here is our 3D graph. And I'm going to do X here, Y here, and Z here. So I know I need to go up 1 and along the Z, and then it's going to extend out 1 in the X direction and 3 in the Y direction. And please know that this is not completely accurate, but it should look something like that. Okay, so you can see that it is 1 in this direction and 3 in that direction. All right, and that's going to be the end of this video. Next video we're going to work on a few more interesting cases with parametrizations.